Hello. This lecture will cover pages 89 through 94 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 7G, Second Order RLC Circuits. Just like the last video, we talked about deriving the response equations for the first order circuits. We're going to derive the response equations for our second order circuits. To begin our analysis, we will consider two basic RLC circuits, and from these circuits derive what we call system equations that lead to the circuit's response equations. We're going to start by looking at a parallel RLC circuit that looks like this. Now, on our responses right here, we're only going to deal with step responses. In other words, step responses in current or step responses in voltages where we're basically just throwing a switch up here. So you can see this value is going to go from 0 up. If it was a switch up here, this value is going to go from 0 to IS as a step response. We're going to see what it does to this circuit, this voltage at this node right here. Keeping in mind there are no initial conditions here. So by looking at the circuit, the current to the inductor at time t equals 0 is equal to the voltage across the capacitor at time t equals 0, and that's going to be equal to 0. There's no current through that inductor, and there's no voltage across that capacitor. By Kirchhoff's current law at this node right here, we see that the currents entering the circuit minus the currents leaving the circuit leaving the node have to equal 0. So this current coming into the top node right here, at this point we'll call via T right here, that voltage, is equal to plus IS minus IR minus IL minus IC equals 0. Writing this in terms of the currents leaving have to equal the currents entering. We note the current across the resistor, if this is via T, is the voltage over the resistance. If you look back on page 11, you might want to stop the video and look back in your lecture notes at page 11. You can see that the current to the inductor is 1 over L, the integral from T0 to T of the voltage across the inductor with respect to time, and the current to the capacitor is C dV dt, and that's equal to I of S. Differentiating this and getting in a standard form where the lead coefficient on the second derivative is 1, we'll divide through by C up here. We get a linear second order differential equation with constant coefficients, and this is what it looks like. The second derivative of the voltage plus 1 over RC, the time constant if you will, the derivative of voltage with respect to time, plus voltage over LC is equal to 1 over C, the derivative of the current in the circuit up here. That's a typical equation, differential equation that you get on a circuit like this with R, L, and C elements in it. Let's look at the next page. A series RLC circuit. Again, no initial conditions here. So again, the current to the inductor at 0 has to equal the voltage across the capacitor at time t equals 0, which is equal to 0. That's what we mean by no initial conditions. I want you to assume that. Notice it's still going to be a step response. We're not going to drive it with a sinusoid right now. We do that later on, and we just concern ourselves with the steady state next chapter. So here we're looking at step response again. We're going to throw a switch up here, and we're going to see what the current in that circuit does. So we're going to do a nodal analysis. We're going to write a loop analysis the way we've done before around the loop, starting at this point. Plus V of S of T minus the voltage across the resistor minus the voltage across the capacitor minus the voltage across the inductor equals 0. We know that the voltage across the resistor is equal to R times I of T. We know that looking back on page 11, we should have this memorized already, the voltage across that capacitor with respect to time is 1 over C, the integral of I dt. And the voltage across the inductor is L di dt equals 0. Rearranging and differentiating and bringing L down to get a standard second order linear differential equation with constant coefficients, it yields this equation down here. Notice if we bring this R to the denominator and form a common fraction down there, that's a time constant down there. The coefficient here of the derivative term in the denominator here has L over R. If we bring this to the bottom, just in passing, I want you to notice that. But I want you to compare this equation here to this equation. It's the same. It's the same form of the equation. It's the same second order linear differential equation with constant coefficients, but the coefficients are different. But it's the same form. Look at that. Look at that. Whether you're solving for voltage on an RLC circuit, or whether you're solving for current in a series RLC circuit. We'll come back to those in a minute. Developing the second order response equations. This is in your book on page 276 to 278, but you probably have a new edition. If you do, it's in chapter 7. You'll see this in chapter 7 if you have trouble with what we're doing here. Once again, the complete solution has two parts. The solution, voltage with respect to time, or current with respect to time, anywhere in the circuit now. I'll let you know where I'm trying to find voltage or current in the problems. But it has a particular solution and has a complementary solution. Well, we don't consider that in electrical engineering in terms of particular solution and complementary solution. It's a steady state solution, and it's your transient solution. So we're going to have, for our total solution on these problems, we're going to have a steady state, and we're going to have a transient. If we drive the circuit with a constant forcing function, the complete solution would look like this, where K1 is equal to the steady state solution, obviously, up here. Keep in mind, we are going to drive these with a constant forcing function, a step response, a voltage or current, where we're closing a switch to a battery or to a source of current or voltage as a step response. We're going to have a constant forcing function. It's going to simplify this. But that's going to be our form. And you'll see that when we get some circuits. You'll look at that and you'll say, yeah, that makes sense. So continuing on here, page number 92, let's look at the solution to the homogeneous equation, which gives us the transient solution. Remember, we're just going to look, just like we did before, it's the homogeneous equation. We're going to set both of these equations right here. We're going to set this equation equal to 0. And we're going to set this equation equal to 0. Both of them. When we do that, we're going to group the coefficients here. And for now, just we'll define these later. But for now, the A1, the coefficient on the first derivative term, is going to be equal to 2 zeta omega 0. That's what we're going to call it. We're going to call it 2 times something called zeta times omega 0. This is going to be a damping ratio, and that's going to be a natural frequency. Don't worry about that now. And the coefficient on this X term out here, voltage or current, is going to be equal to omega 0 squared. Omega 0 squared. So if we make that substitution up here and we put these in for A1 and A2, we end up with this differential equation looking like that. Now we're going to assume the solution to this. We're going to assume the transient solution to this is Ke to the st, just like we did in the first order system. But we're going to convert it to the frequency domain, S of t here. Now, if you remember in some of your math classes, the reason we're going to assume Ke to the st here is in the development for the solution for this first order homogeneous differential equation that we discussed earlier, the solution must be a function whose first and second order derivatives have the same form, so that the left side of the equation will become identically 0 for all t here. So again, that's why we're going to assume this. It's an assumption that's going to work well for us. Making that substitution into this equation here, we get this. we still end up with the ke to the st on each one of these, the second derivative, the first derivative, and then as the function itself out here. Well, that turns out to be perfect because we can divide both sides by ke to the st. They cancel here, and you end up with just your s squared plus 2 zeta omega 0 s plus omega 0 squared equals 0. That is an extremely important equation. That's called the characteristic equation, where zeta is the exponential damping ratio, and omega 0 is called the undamped natural frequency. So we're defining this as zeta now as the exponential damping ratio, and I'll show you where that comes into play in a minute. And omega 0 is the undamped natural frequency. That is just a quadratic equation with the unknowns being s. And you know how to solve characteristic equations. You know how to solve quadratic equations using the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac divided by 2a, something like that. Well, that's all we're going to do to that characteristic equation. So using the quadratic formula to solve the characteristic equation for s, and I do it for you here. Here's your two natural frequencies. There's the one natural frequency, and there's the other natural frequency. All I did was clean these up, and I got them down here in radians per second. That's a natural frequency in radians per second, and that right there is a natural frequency in radians per second. In general, the complementary solution, or this, in this case, the transient solution, because it was a homogeneous equation we're solving here, and this is transient solution, is equal to x of t, or the transient solution, is equal to, or the complementary solution is equal to the transient solution, whether it's void or current, is k1 e to the s1t plus k2 e to the s2t. That's the solution for that second order linear differential equation with constant coefficients. It looks like this, where x of 0 is equal to k1 plus k2. Put 0 in for t up here. You put 0 in for t, you get x of 0 is k1 plus k2. Then take the derivative of this function, set it equal to 0, and you're going to see s1 k1 plus s2 k2. You should be able to look at this and get this. You should be able to look at this, take the derivative. You can do this in your head. So you end up with these two equations. You just solve these two equations simultaneously for k1 and k2, you get your complete solution. You already have s1, you already have s2, you find k1, you find k2, and you have the solution. You have a solution where you can actually plug in a time and determine the current or voltage in the circuit, whether you had that parallel circuit or you had that series circuit. The form of the transient solution depends upon the value of zeta. In the characteristic equation, it depends on the value of zeta. There are three cases to consider. So first thing you're going to do is look at a circuit and get the characteristic equation. It's going to be very easy for you to do that. And then you're going to solve for zeta and omega 0. When you find zeta, if zeta is greater than 1, it's called an overdamped response. And I'll show you what that looks like in a minute. If zeta is less than 1, it's called an underdamped response. And if zeta is equal to 1, it's called a critically damped response. In the next video, we're going to look at each one of these. But you get three different responses. And remember, the natural frequencies are just a solution to the characteristic equation using the quadratic formula. It's this plus this, or it's this minus this. Now, before I show you a couple things finally electrically, let me talk about this in terms of an electromechanical system that you could all appreciate, I think. I'm going to give you an example here of overdamped, underdamped, and critically damped. Matter of fact, I'll give you two examples. I want you to picture getting on an elevator. You're taking an elevator on the first floor to the 20th floor. And the final value is going to be the height. You're looking at the height. You're looking at the distance. And you're going to see what distance does with respect to time. Let's see if I can draw this as you go here. I think that'll make more sense. So I'm going to take a piece of paper here, and I'm going to say that what we're going to do is we're going to take an elevator ride to, I don't know, let's take it to the 100th floor. We'll just pick a number. 100th floor, and the 10th floor. 10th floor, and we're 100 feet up. 10 foot per floor. So what we're going to do is we're going to go up 100 feet. That's 10 floors, and we're going to reach a final value up here of 100 feet, we'll say. Well, this isn't voltage or current. This here is just going to be distance. This is just going to be distance with respect to time on the elevator. And here's time down here. Well, let's say that when you design the electromechanical system, you want to do it so it's very slow and easygoing. You're going to put it in a nursing home, we'll say. So you can go ahead and you can design it so the distance looks like this. You finally get up to the 10th floor at 100 feet. Okay. Now, when you looked at that, that's going to be overdamped. That's going to be the overdamped condition. So what I'm saying is when you're looking at that, you're going to end up with overdamped on the characteristic equation. Zeta is going to be greater than 1. And you'll see this when we work problems. Zeta will be 1.5. Zeta will be 2. Zeta will be 5. But notice it's not for thrill seekers, but it takes a lot of time to get up there. Now, you can design that system so zeta, that electromechanical system in the elevator, is zeta is less than 1. It's 0.7, it's 0.6, or whatever. So, you get up there real fast, but your momentum takes you maybe like that, and you get some ringing. Or maybe it's an overshoot that gets really ridiculous, and it goes like that, and it rings out. Well, you've been on elevators like that. I mean, amusement parks would be great. You're going to the 10th floor, and you're going to go up to 100 feet, but you really go over. You shoot over. The elevator shoots over a little bit and comes down a little bit and rides, and you're going up and down, Finally, you settle on 100 feet, and you can get out of the elevator. You don't design elevators like that. That's going to be this situation. Underdamped. What about critically damped? Critically damped is zeta equal 1, and what happens is you don't have any overshoot, but you come up relatively quickly, and you do something like that. Most elevator designs, I've been told, zeta is equal to 0.707. They design zeta for 0.707 because what that looks like is this. I wish I could do this so you could see it. Let me try doing it with this pen here. This is what zeta 0.707 looks like. You come up with a little bit of overshoot and you come down. Do you see that? That's your zeta equal 0.707 to a step response. The step response is in the elevator. You push a button and it says, boom, go to the 10th floor. That's a signal. Now, if you look in your book, in your last lecture notes, I tried to show you that for a step response up here on page 99, where you have a final value. You don't always have a final value here. But here's your underdamped response. Here's your critically damped response. And here's your overdamped. It's overdamped. The nice thing about a zeta equal 0.707, which some people would argue is pretty close to being the critically damped solution. Very close to this one right here, obviously. Zeta is equal to 0.707, well, 1, but notice it gives you the fastest time with the littlest overshoot. Most elevators are designed like that. Get on an elevator and take it to the 5th floor, or the 2nd floor, or the 10th floor. You'll feel a little bit of overshoot and it'll settle down and you're there. Now, what does that look like in terms of a circuit? Well, we'll be doing that in the lab. And I went ahead and laid this out for you. It looks like this. Let's see where I put it. There it is. We're going to look at the voltage across the capacitor here. We're going to look at the voltage across that capacitor with respect to time. and you close this switch up here at t equals 0. Well, when this switch gets closed at t equals 0 up here, see if I can, I'm not going to get that all on here, but what's going to happen is, depending upon the value of R here, L's already picked at 1 Henry, C is already picked at 100 picofarads, or 100 microfarads. We're going to change the values of R. When we change the value of R in this characteristic equation, you're going to see you may get a voltage that looks like this. You may get a voltage that looks like that. And you may get a voltage that looks like that before it settles out on 12 volts. Before it settles out, you might get a overdamped, you might get a critically damped, or you might get all types of underdamped. And you could see this again on page number 100. If you look at page 100, I gave you nominal values of overshoot and undershoot with zeta equal to 0.7, 0.4, 0.2, 0.1, hard to read, or 2. So this is the transient response of a second order system for a step input. It looks like that to a steady state value. This is normalized, don't forget, normalized. And here's the response to an impulse function where you're just going to shoot it with a pulse and it dies out. But you can see the different responses there. So that's what this would look like. Now, not all of them ends up with a steady state value. I think you can see here when this switch is thrown here and this sits here for a long period of time, this goes to 12 volts at this point. That's 12 volts right there. Well, eventually, this is going to look like an open circuit out here. It's a capacitor. Capacitor looks like an open circuit at time t equal infinity. So the voltage there is going to be no current, so the voltage here is going to equal the voltage there. So the voltage across this capacitor at t equal, as time goes on, is going to, the steady state value is going to be 12 volts. And that's what you see down here, 12 volts. You can reason with that. Now, what about some of the other circuits? If you look in your textbook, they show you what happens if you have this circuit and you want to look at the voltage with respect to time across this element, this here. Well, and it's going to go to 0 because the inductor is going to look like a short. Think about that. So it's going to go to 0. And if you look at the second circuit for the current, see if I can find it real quick. If you're looking at the current in that second circuit, that's what you're solving for here, the current. It's going to go to 0 because that's going to look like an open circuit. The capacitor is going to look like an open circuit at time t equal infinity, or after the transient dies out, so there can't be any current. But you're still going to have a critically damped, an overdamped, and an underdamped response. They're not going to have a final value, so they're going to look like this. And they show this in the textbook. So we're sort of just looking at this right here, if I can get it. They're going to look like this. They're going to go back to 0. So I showed you what happens when you have a steady state value, where you get responses that look like this, and where it's going to decay to 0. If it's underdamped, what's causing this ringing here? Whether it's ringing like this or you're decaying down to 0 and it's ringing like this. What's going to cause the undershoot to negative voltage? It's the transfer of energy between these two elements. They get passed back and forth until they get passed back and forth in this circuit right here between the inductor and the capacitor, and you lose energy each time because the capacitor is eating up that energy, or the resistor is eating that energy up as it's being passed from here to here to here to here in the circuit. You have to think about that, but that's the overall idea. And now we just have to work. We have to look at the three different cases now, and we just work problems. That concludes the lecture.